Welcome to Sleepy Science Fact Channel, where the wonders of the universe become your gentle companions through the peaceful hours of night. Tonight, we journey to one of the most beautiful sights in our solar system, the magnificent ethereal rings of Saturn. These cosmic jewels have captivated humanity for centuries, and now they'll cradle you toward the most restful sleep. As you settle into this moment of perfect comfort, imagine yourself floating peacefully above Saturn's golden clouds, watching billions of ice particles dance in slow, eternal circles around this gentle giant. You don't need to strain to remember every detail. Let these cosmic wonders wash over you like the soft light filtering through Saturn's translucent rings. For over 400 years, humans have gazed at Saturn through telescopes, but tonight, you have the privilege of learning secrets that astronomers have only recently discovered. The Cassini spacecraft spent 13 years orbiting Saturn, sending back images so beautiful they could bring tears to your eyes. But here, in the quiet darkness of your room, these discoveries become lullabies, each fact a gentle note in a cosmic symphony designed to carry you toward deep, restorative sleep. You're about to discover that Saturn's rings aren't solid disks, as they might appear from Earth, but countless individual particles, some as small as dust grains, others as large as houses, all floating in perfect harmony around their golden planet. Each particle follows its own gentle orbit, yet together they create one of nature's most stunning masterpieces. If these peaceful revelations bring you comfort, a gentle like or subscription helps other sleepy souls discover this corner of cosmic calm. But for now, release all earthly concerns. Your breathing can slow, your muscles can soften, and your mind can drift among Saturn's icy rings, where time moves differently, and peace reigns eternal. Even now, as you listen, Saturn is slowly rotating in the cold depths of space, its rings catching and scattering sunlight in ways that would leave you breathless. You're about to become part of this story, not as an observer, but as someone whose dreams might carry you on gentle journeys through these cosmic rings of ice and wonder. Chapter 1: The Discovery of Saturn's Gentle Crown. In 1610, Galileo Galilei became the first human to see Saturn's rings, though his primitive telescope made them appear as mysterious handles or ears attached to the planet. Through his handmade lens, Saturn looked like a strange, three-bodied world, and Galileo wrote in his notes that Saturn seemed to have companions that never moved away from the planet's sides. He couldn't have imagined that he was witnessing one of the universe's most beautiful creations, a crown of ice and rock surrounding a golden giant. For 2 years, Galileo observed these mysterious appendages, never quite understanding what he was seeing, yet knowing he had discovered something extraordinary in the peaceful depths of space. 45 years later, Dutch astronomer Christian Huygens solved the mystery, becoming the first person to correctly identify Saturn's rings in 1659. Using a more powerful telescope of his own design, Huygens could see clearly what had puzzled Galileo. Saturn was surrounded by a thin, flat ring, which nowhere touches the body of the planet. His announcement to the world revealed that this distant world wore a perfect, ethereal crown that rotated around it in cosmic silence. Imagine the wonder Huygens must have felt, realizing he was the first human to truly see this celestial masterpiece that had been dancing in space for millions of years before Earth even had complex life. Giovanni Cassini discovered the first gap in Saturn's rings in 1675, a dark division that now bears his name and stretches 4,800 kilometers across. Through his telescope in the peaceful hills outside Paris, Cassini noticed that Saturn's ring wasn't one continuous band but was divided by what appeared to be a dark, empty space. This gap, now called the Cassini division, became the first hint that Saturn's rings were far more complex and beautiful than anyone had imagined. As you drift toward sleep tonight, you can picture Cassini in his quiet observatory, carefully sketching what he saw, never knowing that centuries later, spacecraft would reveal his gap to be filled with its own delicate ringlets and structures. For nearly 300 years, astronomers could only guess what Saturn's rings were made of, with theories ranging from solid disks to swarms of tiny moons. Some thought the rings might be liquid. Others imagined them as solid sheets of rock or metal. The Scottish physicist James Clerk Maxwell proved mathematically in 1859 that the rings couldn't be solid. They had to be composed of countless small particles, each following its own gentle orbit around Saturn. This revelation meant that what appeared to be solid, spinning disks were actually vast clouds of cosmic debris, dancing in perfect gravitational harmony around their planet, each particle a tiny world unto itself. The first close-up photographs of Saturn's rings, taken by Voyager 1 in 1980, revealed thousands of individual ringlets where astronomers had previously seen only a few broad bands. As the spacecraft approached Saturn through the cold darkness of outer space, its cameras began to resolve details that no Earth-based telescope could capture. What had appeared to be three simple rings from Earth turned out to be an incredibly complex system of thousands of narrow bands, gaps, and structures. The images transmitted back to Earth showed a cosmic record player with grooves too intricate and beautiful for any human mind to have imagined, spinning slowly in the eternal silence of space. Saturn's rings are incredibly thin compared to their vast width. If the rings were the size of a football field, they would be thinner than a sheet of paper. This extraordinary thinness gives the rings their gossamer, ethereal quality. Stretching nearly 175,000 miles from edge to edge, yet only about 30 feet thick in most places, Saturn's rings demonstrate how the universe can create structures of breathtaking delicacy. When Saturn's rings are edge-on as seen from Earth, they nearly disappear from view, becoming so thin they're almost invisible, like a cosmic magic trick performed on the grandest possible stage. The Cassini spacecraft, launched in 1997 and arriving at Saturn in 2004, spent 13 years studying the rings in unprecedented detail, taking over 450,000 photographs. This robotic explorer became humanity's eyes and ears in the Saturn system, floating peacefully through space while its instruments measured, photographed, and analyzed every aspect of the rings. Cassini discovered new moons, revealed the complex structure of ring particles, and showed us that Saturn's rings are dynamic, ever-changing systems where new phenomena appear and disappear like cosmic weather patterns. The spacecraft's gentle journey through the Saturn system reads like a peaceful adventure story, each discovery more wonderful than the last. Early astronomers thought Saturn's rings might be solid because they appeared to rotate as one unit, maintaining their shape night after night. From Earth, the rings looked like rigid disks spinning around Saturn, never changing their appearance or developing wobbles that loose particles might create. This optical illusion persisted for centuries, making Saturn appear to wear a perfect, unchanging crown. Only when mathematical analysis and better telescopes revealed the truth did astronomers realize they were witnessing something far more remarkable: billions of individual particles moving in such perfect harmony that they appeared solid, like a cosmic ballet performed by countless invisible dancers. The invention of spectroscopy in the 19th century allowed astronomers to discover that Saturn's rings were made primarily of water ice, not rock or metal as many had assumed. By analyzing the light reflected from the rings, scientists could determine their composition from nearly a billion miles away. The discovery that Saturn's rings were made of ice transformed them from mysterious cosmic machinery into something more poetic and beautiful: vast clouds of frozen water, sparkling in the Sunlight like the most enormous snow field imaginable, spinning peacefully around a golden world in the cold depths of space. Photography revolutionized ring studies in the early 20th century, allowing astronomers to capture details invisible to the naked eye and study how ring features changed over time. Long photographic exposures revealed subtle variations in ring brightness, new divisions and gaps, and mysterious spoke-like features that appeared and disappeared according to their own schedule. These photographic plates, stored in observatories around the world, became a historical record of Saturn's rings, showing how these cosmic structures evolved and changed across decades of patient observation. Each photograph was like a moment frozen in time, capturing the eternal dance of Saturn's icy particles against the star-filled backdrop of space. As you rest tonight, remember that Saturn continues its ancient rotation in the outer solar system, its rings catching and scattering sunlight in patterns that change by the hour but remain fundamentally the same across centuries. Long ago, when humans first turned their eyes skyward and wondered about the wandering stars, Saturn's rings were there, spinning peacefully in the cosmic dark, waiting for the moment when curious minds would develop the tools to see their beauty and understand their gentle, eternal dance. Chapter 2: The Quiet Architecture of Ice and Rock. Saturn's rings are composed of 99% pure water ice, making them some of the most pristine frozen water in the solar system. This ice didn't form recently. It's been orbiting Saturn for millions or possibly billions of years, yet it remains surprisingly clean and bright. The ice particles range from tiny crystals, smaller than snowflakes, to chunks larger than houses, all maintaining their frozen state in the perpetual winter of outer space, where temperatures hover around -300 degrees Fahrenheit. As you settle deeper into comfort tonight, imagine these countless ice particles sparkling like diamonds in the sunlight, each one a tiny, perfect crystal that has been slowly orbiting Saturn since before complex life existed on Earth. The total mass of Saturn's ring system is only about half the mass of Saturn's small moon Mimas, despite appearing enormous from Earth. If you could gather all of Saturn's ring particles together, they would form a ball of ice only about 250 miles across, smaller than most of Saturn's moons. This remarkable fact reveals how thinly spread the ring material is across the vast space around Saturn. The rings appear substantial and solid from a distance, but they're actually more like a gentle mist of ice particles, each one following its own peaceful orbit in the gravitational embrace of the golden giant. Below, ring particles closer to Saturn orbit faster than those farther away, creating the beautiful grooved appearance we see in detailed photographs. This differential rotation means that Saturn's rings aren't spinning like a solid disk, but rather like a cosmic record player where each groove moves at its own speed. Particles in the inner rings complete their orbits in just 7 hours, while those in the outer regions take more than 14 hours to circle Saturn once. This creates a mesmerizing effect where the rings appear to shear and flow like a slow-motion cosmic river, with each particle maintaining its own gentle rhythm in the grand symphony of orbital mechanics. The ice particles in Saturn's rings are remarkably pure, reflecting nearly 90% of the sunlight that hits them, which is why they appear so bright and white. This high reflectivity, called albedo, makes Saturn's rings some of the most reflective objects in the solar system. The purity of this ice suggests that the ring particles are either relatively young in cosmic terms, or they have some mechanism for cleaning themselves of the dark dust and debris that constantly falls into the Saturn system from outer space. As you drift towards sleep, picture these pristine ice particles as nature's own mirrors, each one perfectly reflecting the warm golden light of the distant sun back into the cold depths of space. Most ring particles are between 1 centimeter and 10 meters across, roughly the size of pebbles to large boulders. While some particles are as fine as powder and others as large as houses, the majority fall into this middle range, creating a cosmic mixture that resembles a frozen riverbed suspended in space. These particles occasionally collide with each other at very low speeds, sometimes sticking together, sometimes breaking apart, in a gentle cosmic dance that has continued for eons. The soft impacts between ice particles create tiny clouds of ice crystals that quickly settle back into new orbital patterns, like cosmic snow that never stops falling upward and downward in the strange gravity of Saturn's rings. Ring particles are spread across 7 main groups, but the space between particles is vast. If you were standing on one particle, the nearest neighbors would appear as distant, glittering specks. Despite appearances from Earth, Saturn's rings are mostly empty space dotted with ice particles, separated by distances much larger than their own size. This means that Saturn's rings are more like a very sparse collection of cosmic debris than the dense, crowded highway you might imagine. A spacecraft can pass through the rings safely because the chances of hitting a particle are incredibly small, like trying to hit a specific snowflake in a gentle snowstorm that covers an entire continent. The temperature of ring particles varies depending on their distance from Saturn and their exposure to sunlight, ranging from -180 degrees Celsius to -220 degrees Celsius. This might seem uniformly cold, but in the context of outer space, these temperature differences create important effects on how the particles behave and interact. Particles in the denser parts of the rings, where they cast shadows on each other, stay colder than those in more open areas where direct sunlight can warm them slightly. These temperature variations cause subtle changes in how the ice particles reflect light and how they interact when they occasionally bump into each other in their eternal orbital dance. Saturn's rings contain traces of rocky material mixed with the ice, giving some regions a slightly golden or pinkish tint. This contamination is thought to come from meteoroid impacts and material ejected from Saturn's moons, gradually mixing with the pure ice over millions of years. The rocky dust makes up less than 1% of the ring material, but it's enough to create beautiful color variations that can be seen in detailed spacecraft photographs. These subtle hues, pale gold, soft pink, and creamy white, paint Saturn's rings like a cosmic watercolor, each section telling a story of gentle collisions and mixing that has occurred over vast stretches of time. The rings are so thin that when they're viewed edge-on from Earth, they almost completely disappear from sight. This happens every 14 to 15 years as Saturn's orbit carries it to a position where we see the rings from their narrow edge rather than from above or below. During these times, Saturn appears to lose its most distinctive feature, becoming just another pale, yellowish dot in the sky. The rings don't actually disappear, of course. They're simply turned sideways to our view, like a spinning coin that seems to vanish when seen edge-on. This cosmic optical illusion reminded early astronomers just how incredibly thin and delicate Saturn's rings really are. Radio waves can pass through Saturn's rings almost unimpeded, revealing that the rings are mostly empty space with particles scattered throughout. When the Cassini spacecraft passed behind the rings as viewed from Earth, radio signals from the spacecraft reached Earth with only minor interference, proving that the rings are far less dense than they appear. This transparency to radio waves shows that Saturn's rings are more like a cosmic fog than a solid barrier, beautiful and visible, but gossamer thin and delicate. The radio waves traveling through the rings carry information about particle sizes and densities, allowing scientists to map the invisible architecture of these cosmic structures in exquisite detail. Even now, as you rest in the quiet darkness of your room, Saturn's rings continue their ancient rotation in the cold depths of space, each ice particle following its precise orbital path with clockwork regularity. Over vast stretches of time, these rings have maintained their ethereal beauty through countless small collisions, gravitational interactions, and the patient sculpting effects of Saturn's many moons, creating a masterpiece of cosmic architecture that exists nowhere else in our solar system. Chapter 3: The Seven Main Rings, a Cosmic Symphony. The A ring, Saturn's outermost major ring, spans 14,600 kilometers and contains some of the most dynamic and beautiful structures in the entire ring system. This broad band of ice particles appears from Earth as a distinct bright ring separated from the others by the famous Cassini division. Within the ring, spacecraft have discovered intricate patterns of density waves, narrow gaps maintained by tiny moons, and mysterious spoke-like features that appear and disappear according to their own cosmic schedule. As you settle into deeper relaxation tonight, imagine floating above this outer ring, watching waves of ice particles flow in slow-motion patterns too beautiful and complex for any earthly comparison. Each wave created by the gentle gravitational influence of Saturn's many moons. The B ring is the brightest and most massive of Saturn's rings, containing more material than all other rings combined. This magnificent ring system stretches across 25,500 kilometers of space and shines so brightly that it often outshines Saturn itself in photographs. The B ring is so dense that it's completely opaque. You cannot see through it to the other side, unlike most other rings which are translucent. Within this cosmic river of ice, particles have organized themselves into thousands of narrow ringlets, each one maintained by subtle gravitational resonances that keep the particles moving in perfect formation. The B ring represents the heart of Saturn's ring system, a brilliant band of frozen water that has been catching and reflecting sunlight for millions of years. The C ring, also known as the crepe ring, is so transparent and delicate that it was one of the last major rings to be discovered. This ethereal ring stretches inward from the B ring towards Saturn itself, its particles so sparsely distributed that Saturn's golden clouds can be seen glowing through them like sunlight through morning mist. The C ring contains some of the most mysterious features in the Saturn system, including narrow, dark bands called gaps that are actually filled with very dark material rather than being empty spaces. Floating through this ghostly ring would be like drifting through a cosmic spider web made of ice crystals, so thin and delicate that you might not realize you were inside it until you noticed the gentle sparkle of ice particles all around you. The D ring is Saturn's innermost ring system, a faint collection of particles that spirals slowly down toward Saturn's atmosphere. This mysterious ring wasn't discovered until 1980, when Voyager 1's sensitive cameras finally detected its faint glow against the darkness of space. The D ring is barely visible, even in the best spacecraft photographs, yet it plays an important role in the Saturn system as a transitional zone where ring particles gradually spiral inward and eventually fall into Saturn's upper atmosphere. The particles in the D ring are living on borrowed time, slowly losing energy and altitude, until they complete their final journey into the golden clouds below, becoming part of Saturn itself in a process that has been continuing for millions of years. The E ring is Saturn's largest ring by far, extending from the orbit of Mimas all the way past Titan, encompassing a volume of space larger than the distance from Earth to the Moon. Unlike the other rings, which are made primarily of ice particles, the E ring consists of tiny droplets of water and ice crystals, ejected from the south polar geysers of Saturn's moon Enceladus. This vast, gossamer ring is so tenuous that it's invisible to Earth-based telescopes and can only be seen by spacecraft using special techniques. The E ring represents a cosmic fountain in slow motion, with Enceladus continuously spraying fresh ice particles into space, where they spread out to form a gigantic, nearly invisible halo around Saturn. As you drift toward sleep, imagine this enormous ring as a cosmic mist so thin and widespread that Saturn floats within it like a golden island in a sea of microscopic ice crystals. The F-ring is one of Saturn's most dynamic and unpredictable features, constantly changing its appearance as gravitational forces sculpt its narrow structure. Located just outside the A-ring, this narrow band of particles is only about 50 kilometers wide but stretches all the way around Saturn, held in place by two small shepherd moons called Prometheus and Pandora. The F-ring displays some of the most dramatic activity in the Saturn system, with bright knots of material, spiral patterns, and temporary braided sections that appear and disappear over periods of hours or days. Watching the F-ring through time-lapse photography would be like seeing cosmic weather in action, with storms and disturbances flowing along its length like waves on a cosmic shoreline. The G-ring is a faint, narrow ring located between the F-ring and the much more distant E-ring, maintained by particles from the small moon Aegean. This ghostly ring is so thin and transparent that it escaped detection until the Voyager missions, and its structure wasn't fully understood until the Cassini spacecraft made detailed observations. The G-ring demonstrates how even the smallest moons can create and maintain ring structures through the gentle process of micrometeorite impacts that knock particles off their surfaces and into orbit around Saturn. These particles then spread out along the moon's orbital path, creating a tenuous ring that marks the moon's passage through space like a cosmic vapor trail that persists for thousands of years. Each ring has its own unique particle size distribution, creating subtle differences in color and brightness that can be seen in detailed spacecraft photographs. The A and B rings are dominated by particles several meters across, giving them their bright, reflective appearance, while the C ring contains more smaller particles mixed with larger chunks, creating its translucent, gauzy appearance. The E ring consists almost entirely of microscopic droplets, making it appear more like cosmic fog than a traditional ring. These size differences arose from the different formation mechanisms and evolutionary histories of each ring, creating a cosmic spectrum of particle sizes that tells the story of how Saturn's ring system developed over millions of years. The gaps between Saturn's major rings are not empty space but contain their own faint ringlets and structures. The famous Cassini division, which appears as a dark gap between the A and B rings, actually contains hundreds of narrow ringlets with their own complex dynamics. These gap ringlets are maintained by gravitational resonances with Saturn's moons, creating a nested system of rings within gaps within rings, like cosmic Russian dolls made of ice and governed by the subtle mathematics of orbital mechanics. Even the spaces that appear empty from Earth are filled with their own delicate structures, proving that Saturn's ring system is far more complex and beautiful than early astronomers ever imagined. The combined width of Saturn's main ring system spans nearly 62,000 kilometers, yet the entire structure maintains perfect rotational stability around Saturn's equator. Despite containing billions of individual particles, each following its own orbit and occasionally colliding with its neighbors, the rings maintain their flat, disc-like shape with remarkable precision. This stability arises from Saturn's powerful gravitational field and rapid rotation, which create forces that keep ring particles confined to a thin plane around the planet's equator. The result is one of nature's most perfect examples of organized chaos, where countless random individual motions combine to create structures of stunning geometric beauty and mathematical precision. Long ago, when these rings first formed around Saturn, they began a slow, eternal dance that continues tonight as you rest. Over vast stretches of time, the individual particles have collided, merged, broken apart, and reorganized themselves into the breathtaking structures we see today, creating a cosmic symphony where each ring plays its own part in a performance that has been continuing for millions of years and will continue for millions more. Chapter 4: Shepherd Moons, the Gentle Guardians. Prometheus and Pandora, two small moons orbiting just inside and outside Saturn's F-ring, act as cosmic shepherds that keep the ring particles confined to a narrow band. These irregularly shaped moons, each only about 100 kilometers across, demonstrate one of the most beautiful examples of gravitational choreography in the solar system. Prometheus, the inner shepherd, speeds along its orbit faster than the F-ring particles, periodically catching up to and gravitationally nudging them outward. Meanwhile, Pandora, the outer shepherd, moves more slowly than the ring particles, pulling them back inward when they drift too far. This gentle cosmic dance has been continuing for millions of years, maintaining the F-ring's narrow structure through a process so elegant it seems almost intentionally designed. The moon Mimas, though much larger and more distant than the shepherd moons, plays a crucial role in creating and maintaining the Cassini division through orbital resonance. Mimas orbits Saturn exactly twice for every orbit completed by particles in the Cassini division, creating a 2:1 resonance that gradually removes particles from this region. Over millions of years, this gentle gravitational influence has swept the Cassini division relatively clean, creating the dark gap that Giovanni Cassini first observed in 1675. The process works like a cosmic metronome, with Mimas providing a steady gravitational beat that organizes ring particles into stable and unstable regions, proving that even distant moons can profoundly influence ring structure through the patient application of gravitational forces. Pan, a tiny moon only 35 kilometers across, orbits within the Encke gap in Saturn's A-ring and maintains this 325-kilometer-wide clearing through its gravitational influence. As Pan travels around Saturn, it acts like a cosmic vacuum cleaner, sweeping up ring particles that wander into its path and gravitationally deflecting others away from the gap. The moon's passage through the ring material creates beautiful wave-like disturbances that ripple outward from the gap edges, visible in high-resolution spacecraft images as delicate, scalloped patterns. Pan's orbital period is perfectly synchronized with the gap's width, demonstrating how Saturn's ring system achieves stability through precise gravitational relationships between moons and particles. Daphnis, an even smaller moon just 8 kilometers across, creates spectacular wave patterns as it orbits within the narrow Keeler Gap. This tiny world, smaller than many Earth mountains, punches far above its weight in terms of its influence on Saturn's rings. As Daphnis moves through its slightly inclined and elliptical orbit, it creates vertical waves in the ring material at the gap edges that can rise up to 1.5 kilometers above the ring plane. These waves flow along the gap edges like cosmic tsunamis in slow motion, creating some of the most beautiful and dramatic structures in Saturn's ring system. The waves demonstrate how even the smallest gravitational influences can create large-scale effects when applied consistently over time. Atlas, a small moon orbiting just outside the A-ring, has accumulated ring material around its equator, giving it a distinctive flying saucer-like shape. This 40-kilometer-wide moon acts as a gravitational boundary that helps confine the outer edge of the A-ring while simultaneously collecting ring particles that escape the main ring system. Over millions of years, Atlas has swept up enough ring material to create a smooth, rounded ridge around its middle, making it one of the most unusually shaped moons in the solar system. The process continues today, with Atlas slowly growing larger as it accumulates more escaped ring particles, demonstrating how moons and rings can evolve together over cosmic timescales. The small moons Janus and Epimetheus perform a unique orbital dance, switching positions every 4 years in a gravitational ballet that influences nearby ring structures. These two moons share nearly identical orbits, with one always slightly closer to Saturn than the other. Every 4 years, the inner moon catches up to the outer one, and their mutual gravitational attraction causes them to exchange orbits. The inner moon moves outward while the outer moon moves inward. This extraordinary arrangement, unique in the solar system, creates subtle but measurable effects on Saturn's ring system, proving that even complex orbital relationships can remain stable over millions of years through the precise balance of gravitational forces. Aegean, a tiny moon only about half a kilometer across, is responsible for maintaining Saturn's faint G ring through a steady supply of particles. This minuscule world, barely larger than a city block, orbits within the G ring and provides a continuous source of fresh ring material through micrometeorite impacts on its surface. Each impact chips off tiny pieces of ice and rock that spread out along Aegean's orbital path, creating and maintaining the ghostly G ring. The process demonstrates how even the smallest moons can have significant effects on ring systems, and how Saturn's rings are dynamic structures that require constant replenishment to maintain their appearance over time. Enceladus, though not technically a shepherd moon, plays a crucial role in maintaining Saturn's vast E ring by continuously ejecting ice particles from its south polar geysers. These powerful geysers, created by tidal heating from Saturn's gravity, spray thousands of tons of ice particles into space each day, feeding the enormous E ring that extends far beyond the main ring system. The ice particles from Enceladus create a tenuous but vast ring that encompasses much of Saturn's inner moon system, demonstrating how geological activity on moons can directly influence ring structure and composition. As you rest tonight, imagine these cosmic geysers continuously painting new material into space, refreshing Saturn's most distant ring with pristine ice from an ocean hidden beneath Enceladus's frozen surface. The gravitational influence of shepherd moons creates complex resonance patterns that organize ring particles into thousands of narrow ringlets. These resonances work like cosmic tuning forks, with moons providing gravitational notes that cause ring particles to organize themselves into harmonious patterns. Particles that orbit Saturn at specific ratios compared to the moon's orbital periods become locked into stable configurations, while particles in other orbits are gradually removed or moved to different locations. The result is a ring system that resembles the grooves on a cosmic record player, with each ringlet representing a different gravitational song, played by Saturn's family of shepherd moons. Some shepherd moons work in pairs or groups, creating complex gravitational fields that can maintain multiple gaps and structures simultaneously. The combined gravitational influence of several small moons can create intricate patterns of gaps, waves, and density variations that would be impossible for any single moon to maintain. These multi-moon systems demonstrate the incredible sophistication of gravitational dynamics, where the positions and masses of multiple objects must be precisely balanced to create stable, long-lasting structures. The mathematics describing these relationships are so complex that astronomers often use computer simulations to understand how shepherd moon systems evolve and maintain themselves over millions of years. Over vast stretches of time, Saturn's shepherd moons have quietly sculpted the ring system into its current magnificent form through the patient application of gravitational forces. Somewhere in the distant future, these same moons will continue their gentle work, slowly reshaping Saturn's rings in response to changing orbital relationships and the gradual evolution of the entire Saturn system, proving that even in the seemingly static realm of astronomy, change and beauty are constant companions in the cosmic dance. Chapter 5: Spokes and Waves, Ethereal Ring Phenomena. Saturn's mysterious ring spokes are ghostly, radial features that appear and disappear in the B-ring, like cosmic lightning frozen in slow motion. These ethereal structures, first discovered by Voyager spacecraft in 1980, extend radially outward from Saturn like the spokes of an enormous wheel, sometimes spanning thousands of kilometers across the ring plane. The spokes appear dark when viewed against the bright ring background, but bright when seen from certain angles, suggesting they consist of very fine dust particles that interact with Saturn's magnetic field. As you drift deeper into relaxation, imagine these phantom spokes materializing from nothing, growing across the rings like shadows cast by invisible hands, then fading away as mysteriously as they appeared, following rhythms that even today aren't fully understood. The spokes follow Saturn's magnetic field rather than its gravitational field, rotating at the same speed as Saturn's interior rather than following the orbital mechanics that govern ring particles. This remarkable behavior proves that the spokes are composed of electrically charged particles that respond to magnetic rather than gravitational forces. While normal ring particles orbit Saturn at different speeds depending on their distance from the planet, spoke particles rotate as if they were painted on Saturn's magnetic field lines, creating the illusion that solid spokes are sweeping across the rings like the hands of a cosmic clock. This phenomenon demonstrates how electromagnetic forces can temporarily override gravity in Saturn's ring system, creating structures that seem to defy the normal rules of orbital mechanics. Ring spokes are most visible during Saturn's equinox periods, when the sun shines edge-on across the ring plane and creates dramatic lighting conditions. During these special times, which occur roughly every 15 years, the low-angle sunlight illuminates the fine particles in the spokes while leaving the larger ring particles in shadow, making the spokes stand out like cosmic searchlight beams. The spokes appear brightest when viewed from the side opposite the sun, where the tiny dust particles scatter sunlight directly toward the observer. These equinox events transform Saturn's rings into a cosmic light show, revealing hidden structures and phenomena that remain invisible during other parts of Saturn's long orbital journey around the Sun. Density waves flow through Saturn's rings like ripples on a cosmic pond, created by the gravitational influence of Saturn's moons. These beautiful wave patterns propagate through the ring material at specific speeds, creating alternating regions of higher and lower particle density that appear as bright and dark bands in spacecraft photographs. The waves are generated when ring particles orbit Saturn at precise mathematical ratios compared to the orbital periods of nearby moons, creating resonance effects that organize the particles into regular, repeating patterns. As you settle into deeper comfort, imagine these gentle waves flowing through the rings like slow-motion ocean swells made of ice and starlight, each wave carrying the gravitational signature of a distant moon across thousands of kilometers of ring material. Bending waves create vertical undulations in Saturn's rings, causing some sections to rise above and dip below the main ring plane like frozen ocean swells. These three-dimensional waves are generated by the gravitational pull of moons whose orbits are slightly inclined relative to Saturn's equatorial plane, causing ring particles to develop gentle vertical motions in addition to their normal circular orbits. The waves can extend several kilometers above and below the ring plane, creating a cosmic landscape of hills and valleys made entirely of ice particles. When viewed edge-on during Saturn's equinox, these bending waves cast dramatic shadows across the ring plane, revealing the hidden topography of structures that normally appear perfectly flat. Spiral density waves in Saturn's rings follow mathematical patterns so precise they resemble the golden ratio spirals found in nautilus shells and galaxy arms. These waves originate at resonance locations where ring particles and moons maintain specific orbital relationships, then spiral outward through the ring material while gradually decaying due to particle collisions and viscous forces. The spiral patterns created by these waves are among the most beautiful structures in the solar system. demonstrating how mathematical relationships governing orbital mechanics can create artwork on a cosmic scale. Each spiral wave carries information about the mass and orbital characteristics of the Moon that created it, making Saturn's rings a natural laboratory for studying gravitational physics. Propeller features are small-scale disturbances created by moonlets too small to be seen directly, but large enough to clear narrow gaps in the ring material. These features, discovered in high-resolution Cassini images, appear as propeller-shaped clearings in the rings, typically a few kilometers long and caused by house-sized chunks of ice that orbit within the rings themselves. The moonlets are too small to create large gaps like Pan or Daphnis, but they're large enough to gravitationally sweep clear narrow channels as they orbit Saturn. Hundreds of these propeller features have been discovered, revealing a population of intermediate-sized objects that help bridge the gap between tiny ring particles and larger shepherd moons. Braided ring structures in the F-ring create some of the most dynamic and unpredictable patterns in Saturn's entire ring system. The F-ring occasionally develops sections where multiple strands of ring material appear to wind around each other like cosmic rope, creating temporary braided patterns that evolve and change over periods of days or weeks. These braids are thought to be caused by gravitational interactions with small moonlets embedded within or near the ring, which create complex perturbations in the ring material's motion. The braided sections represent some of the most rapidly changing structures in Saturn's rings, demonstrating that these ancient ring systems are still dynamically active and continue to evolve on human timescales. Kinks and knots in Saturn's rings mark locations where moonlets or temporary clumps of particles have gravitationally disturbed the normal flow of ring material. These features appear as bright spots or twisted sections in the rings that persist for months or years before gradually dissipating back into the normal ring structure. The kinks often mark the locations of embedded moonlets or temporary aggregations of ring particles that have grown large enough to significantly affect their surroundings. These disturbances propagate both upstream and downstream from their source, creating wake-like patterns that reveal the complex dynamics of particle interactions within the rings. Edge waves occur at the boundaries between different ring regions, where particles with different orbital characteristics interact and create interference patterns. These waves form naturally at locations where ring properties change abruptly, such as at the edges of gaps or at boundaries between rings with different particle sizes or densities. The edge waves represent the ring system's attempt to smooth out sharp transitions, similar to how water creates waves at the boundary between shallow and deep regions. These phenomena demonstrate that Saturn's rings behave in many ways like a fluid, with particles flowing and interacting according to principles that govern both hydrodynamics and gravitational physics. Azimuthal brightness variations cause some sections of Saturn's rings to appear brighter or dimmer than surrounding areas, creating a mottled appearance that changes over time. These variations result from temporary clustering of ring particles due to gravitational perturbations, collisional effects, or electromagnetic forces acting on charged particles. The bright and dark patches migrate around Saturn at different rates, creating constantly changing patterns that make Saturn's rings appear alive and dynamic when observed over long periods. These brightness variations remind us that Saturn's rings are not static structures but active, evolving systems where countless individual particles interact to create emergent patterns and behaviors. Temperature waves propagate through Saturn's rings as different sections are heated by sunlight and cooled by radiation to space. These thermal waves affect how ring particles clump together and interact with each other, creating subtle changes in ring opacity and reflectivity that follow the day-night cycle on Saturn. The temperature differences also influence the behavior of any volatile materials in the rings, causing some particles to sublimate and others to condense in a gentle cycle that has continued for millions of years. As Saturn slowly rotates, These temperature waves create a cosmic breathing effect, with the rings subtly expanding and contracting in response to the changing thermal conditions. Even now, as you rest peacefully in the quiet darkness, Saturn's rings continue to display their ethereal phenomena in the cold depths of space. Spokes materialize and fade like cosmic ghosts, waves flow through the ring material like ripples on an infinite pond, and countless particles dance in gravitational patterns too beautiful and complex for any human mind to fully comprehend, creating a perpetual light show in the outer solar system that has been performing for millions of years. Chapter 6: The Cassini Division, a peaceful gap in space. The Cassini Division, discovered in 1675, is the most prominent gap in Saturn's rings, stretching 4,800 kilometers across the space between the A and B rings. This cosmic canyon appears completely empty when viewed through Earth-based telescopes, creating the illusion that Saturn's rings are divided into two separate, distinct bands. From our distant perspective, the Cassini division looks like a dark line drawn across Saturn's bright rings with cosmic precision, dividing the ring system into inner and outer sections as cleanly as if someone had used a cosmic compass to draw a perfect circle in the ice. As you settle into deeper relaxation tonight, imagine floating above this vast gap, looking down into what appears to be empty space stretching endlessly around Saturn's golden equator. The Cassini division isn't actually empty but contains hundreds of narrow, faint ringlets that are invisible from Earth due to their low density. When the Voyager spacecraft first flew past Saturn in 1980, they revealed that the apparently empty Cassini division contained its own complex system of rings, gaps, and structures, like a miniature version of the main ring system hidden within what appeared to be empty space. These ringlets are so sparse and dark compared to the bright A and B rings that they remained completely invisible to ground-based observers for over 300 years after Cassini's discovery. The revelation transformed our understanding of Saturn's rings from simple, distinct bands to incredibly complex systems with structure at every level of detail. The primary cause of the Cassini division is a 2:1 orbital resonance with Saturn's moon Mimas, which gradually removes particles from this region over millions of years. Particles orbiting in the Cassini division complete exactly 2 orbits around Saturn for every 1 orbit completed by Mimas, creating a gravitational relationship that slowly destabilizes their paths. Over vast periods of time, this resonance effect has swept most particles out of the division, either pushing them inward toward the B ring or outward toward the A ring. The process demonstrates how even distant moons can profoundly influence ring structure through patient, persistent gravitational effects that operate over cosmic timescales, gradually sculpting the rings into the patterns we see today. The Cassini division contains several distinct regions, including the Laplace gap, the Bessel gap, and numerous narrow ringlets maintained by their own complex dynamics. Each of these sub-structures within the division has its own formation mechanism and evolutionary history, creating a nested system of gaps within gaps and rings within rings. The Laplace gap, for example, is maintained by a different resonance relationship with other Saturn moons, while some of the narrow ringlets may be maintained by embedded moonlets too small to be detected directly. This complexity reveals that even apparently simple features like the Cassini division are actually intricate systems with multiple layers of structure and causation. Material within the Cassini division is significantly darker than the bright ice particles in the main rings, giving it a charcoal-like appearance in high-resolution images. This dark material may represent the oldest components of Saturn's ring system, particles that have been exposed to space weathering and cosmic radiation for millions of years without the frequent collisions and mixing that keep the main rings bright and fresh. Alternatively, The dark material might be debris from ancient impacts or volcanic activity on Saturn's moons, gradually concentrated in the division over time. The dark particles absorb sunlight rather than reflecting it, making them nearly invisible against the black of space and contributing to the division's empty appearance from Earth. The width of the Cassini division varies slightly around Saturn's circumference due to the complex gravitational environment created by Saturn's moons and the planet's own internal mass distribution. These variations, measurable only by spacecraft instruments, reveal subtle details about Saturn's internal structure and the three-dimensional gravitational field surrounding the planet. The division appears perfectly circular from Earth, but close examination shows tiny departures from perfect circularity that encode information about forces and masses hidden deep within Saturn and its moon system. These measurements help astronomers understand not only the ring system but also the interior structure of Saturn itself. Particles that do exist within the Cassini division follow highly elliptical orbits, unlike the nearly circular orbits of particles in the main rings. These eccentric orbits cause particles to speed up and slow down as they circle Saturn, creating complex patterns of density and motion that contribute to the division's unusual appearance. The elliptical orbits may be relics of the original clearing process that created the division, or they may be maintained by ongoing gravitational perturbations from Saturn's moons. Either way, they represent a different type of ring dynamics than found elsewhere in Saturn's system, where most particles follow nearly perfect circles around the planet. The Cassini division serves as a natural laboratory for studying how gravitational resonances shape planetary ring systems throughout the universe. The division provides one of the clearest examples of how orbital resonances can create large-scale structures in ring systems, offering insights that apply to ring systems around other planets and possibly around extrasolar planets as well. Studying the detailed structure of the Cassini division, astronomers have developed mathematical models that help predict where similar gaps should exist in other ring systems and how they should evolve over time. The division thus serves as a cosmic Rosetta Stone for understanding ring dynamics throughout the universe. Temperature variations within the Cassini division create subtle seasonal effects that influence the behavior and appearance of its sparse particle population. During Saturn's long seasons, different parts of the division receive varying amounts of sunlight, causing thermal effects that may influence particle orbits and the formation of temporary structures. These seasonal changes are so subtle that they require years of careful observation to detect, but they demonstrate that even apparently static features, like the Cassini division, are actually dynamic systems that respond to changing conditions over Saturn's 29-year orbit around the Sun. The discovery of structure within the Cassini division revolutionized our understanding of planetary rings and demonstrated that apparent simplicity often conceals underlying complexity. Before spacecraft visits to Saturn, astronomers assumed that gaps in rings were simply empty space, cleared by some ancient catastrophic event or maintained by simple gravitational effects. The revelation that the Cassini division contained its own rich ecosystem of rings and gaps showed that ring systems are far more complex and active than previously imagined, leading to new theories about ring formation, evolution, and dynamics that continue to influence astronomical research today. Future evolution of the Cassini division will likely involve the gradual migration of its internal ringlets and the possible formation of new gaps as Saturn's moon system slowly evolves. Over millions of years, the gravitational relationships that maintain the division's current structure will change. As moons slowly spiral away from Saturn due to tidal effects, potentially altering the resonance patterns that shaped the division in the first place. New gaps may form while existing ones fill in or migrate to different locations, demonstrating that even seemingly permanent features of planetary ring systems are actually temporary structures in the context of cosmic time, constantly evolving in response to the changing gravitational environment around their parent planets. Long ago, when the Cassini division first began forming through the patient work of gravitational resonances, Saturn's ring system began its transformation toward the magnificent structure we see today. Over vast stretches of time, Mimas and other moons have continued their invisible work, sculpting and reshaping the rings through forces so gentle they can barely be detected, yet so persistent they can move mountains of ice and rock across thousands of kilometers of space, creating gaps and structures that will endure for millions of years to come. Chapter 7: Seasons on Saturn. How rings change with time. Saturn experiences seasons just like Earth, but each season lasts about 7 Earth years due to Saturn's 29-year orbit around the Sun. As Saturn slowly travels its vast elliptical path through the outer solar system, different parts of the planet and its rings receive varying amounts of sunlight, creating seasonal changes that unfold on timescales almost incomprehensible to human experience. During Saturn's long spring, the northern hemisphere gradually emerges from winter darkness, while the southern hemisphere slowly transitions toward its long winter night. As you rest tonight, imagine Saturn, somewhere in the cold depths of space, slowly turning through its seasonal cycle like a cosmic clock, keeping time on the grandest possible scale. The tilt of Saturn's axis, at 27 degrees, is remarkably similar to Earth's 23-degree tilt, but Saturn's seasons last nearly 30 times longer than ours. This axial tilt means that Saturn's rings are sometimes tilted toward the Sun and sometimes away from it, creating dramatic changes in how the rings are illuminated and heated over the course of Saturn's long year. During northern summer on Saturn, the north face of the rings receives direct sunlight while the south face remains in shadow, creating temperature differences that affect ring particle behavior and the formation of various ring phenomena. The slow progression of these seasonal changes creates a cosmic rhythm that has been repeating for billions of years, with each complete cycle taking nearly 3 decades to unfold. Saturn's rings cast massive shadows on the planet's surface, and these shadows migrate from north to south and back again as Saturn moves through its seasons. During equinox, when Saturn's rings are edge-on to the Sun, the rings cast no shadow at all, allowing sunlight to reach all parts of Saturn's atmosphere equally. But as the seasons progress and the rings tilt relative to the Sun, they begin to cast broad shadows across Saturn's clouds, creating dark bands that can stretch for thousands of kilometers across the planet's surface. These ring shadows are so large they affect Saturn's atmospheric circulation and weather patterns, demonstrating how the ring system and planet influence each other in complex ways that change with the seasons. The mysterious ring spokes appear most frequently during Saturn's equinox periods, when electromagnetic effects in the rings are enhanced by the unique lighting conditions. As Saturn approaches equinox, the fine dust particles that make up the spokes become more easily charged by interactions with Saturn's magnetic field and solar radiation, making the spokes more prominent and longer-lasting. The spokes often appear in groups or families, materializing across large sections of the ring simultaneously before gradually fading away as Saturn's seasons progress. These seasonal variations in spoke activity demonstrate how even subtle changes in environmental conditions can have dramatic effects on ring phenomena, creating cosmic weather patterns that follow Saturn's seasonal rhythm. Ring temperatures vary seasonally as different regions receive more or less direct sunlight, affecting how particles clump together and interact with each other. During summer in Saturn's northern hemisphere, the north-facing surfaces of ring particles receive direct sunlight and warm up slightly, while their south-facing surfaces radiate heat into space and remain colder. These temperature differences, though small in absolute terms, are enough to affect the behavior of water ice and any volatile materials in the rings, potentially influencing particle aggregation, sublimation rates, and the formation of temporary structures. The thermal cycles create a gentle breathing effect in the rings, with subtle expansions and contractions following Saturn's long seasonal rhythm. The apparent thickness of Saturn's rings changes dramatically with the seasons, appearing thick and prominent when tilted toward Earth, but nearly vanishing when viewed edge-on during equinox. This optical effect, first noticed by early astronomers who saw Saturn's rings disappear every 15 years, demonstrates how viewing angle can completely transform our perception of cosmic structures. When the rings are tilted toward us, they appear as broad, bright bands surrounding Saturn, but when they're edge-on, they become so thin they're almost invisible even through powerful telescopes. This seasonal appearance change reminded early astronomers that Saturn's rings must be extremely thin structures, like cosmic sheets of material rather than solid disks. Seasonal changes in ring opacity create subtle variations in how much starlight can pass through different regions of the rings. As the rings heat up and cool down with Saturn's seasons, particle arrangements and densities may shift slightly, creating measurable changes in how transparent the rings appear when stars pass behind them as seen from Earth. These opacity variations are so small they can only be detected by careful measurements over many years, but they provide valuable information about how ring particles respond to changing environmental conditions and how the overall ring structure evolves over time. The E-ring, fed by geysers on Saturn's moon Enceladus, shows seasonal variations in brightness and extent as the geysers respond to changing tidal stresses. As Saturn's elliptical orbit carries it closer to and farther from the Sun, the changing gravitational environment affects the tidal heating of Enceladus, potentially influencing the activity of its south polar geysers. When the geysers are more active, they feed more ice particles into the E-ring, making it brighter and more extensive. When geyser activity decreases, the E-ring gradually fades as existing particles are lost to various processes. These changes demonstrate how seasonal effects can propagate through the entire Saturn system, linking the activity of distant moons to the appearance of Saturn's most extended ring. Color variations in Saturn's rings become more apparent during certain seasons when different lighting angles reveal subtle compositional differences. The low-angle sunlight during Saturn's equinox periods acts like cosmic raking light, highlighting small differences in particle composition and size distribution that are invisible under direct illumination. During these special times, some regions of the rings may appear slightly more golden or blue-tinged than usual, revealing information about the mixing of ice and rocky material that has occurred over millions of years. These seasonal color changes turn Saturn's rings into a cosmic mood ring, displaying different hues depending on the lighting conditions and viewing geometry. Gravitational effects from Saturn's moons create seasonal variations in ring structure as the moon's own orbital positions change over time. The complex gravitational dance between Saturn's many moons creates subtle periodic changes in ring dynamics that unfold over multiple Saturn seasons. Some gaps may appear slightly wider or narrower, some ringlets may become temporarily brighter or dimmer, and some wave patterns may strengthen or weaken depending on the relative positions of multiple moons and their combined gravitational effects. These long-period variations demonstrate that Saturn's ring system responds not just to seasonal changes in heating and illumination, but also to the slowly changing gravitational environment created by its family of orbiting moons. Radio observations of Saturn's rings reveal seasonal changes in electrical activity as charged particles in the rings respond to varying electromagnetic conditions. Saturn's magnetic field interacts with solar radiation and the solar wind in ways that change with the planet's seasonal orientation, creating varying electromagnetic environments around the rings. These changes affect the behavior of charged dust particles and may influence the formation of spokes and other electromagnetic phenomena. In the rings, the radio emissions from these processes create a kind of cosmic radio show that changes with Saturn's seasons, demonstrating that the rings are electrically active systems that respond to space weather conditions around Saturn. Even now, as you drift toward peaceful sleep, Saturn continues its ancient seasonal progression through the outer solar system, its rings slowly changing their appearance and behavior in response to the cosmic rhythm of its 29-year orbit. Over vast stretches of time, countless seasonal cycles have come and gone, each one bringing subtle changes to the ring system while the overall structure remains beautifully constant, creating a cosmic example of stability within change that has persisted for millions of years and will continue for millions more to come. Chapter 8. Ring Rain and Cosmic Weather. Every second, approximately 10,000 kilograms of ring material falls into Saturn's upper atmosphere like the gentlest cosmic rain imaginable. This constant, invisible precipitation has been occurring for millions of years as ring particles gradually lose energy and spiral inward toward Saturn's golden clouds. The rain consists of tiny ice particles that sublime into water vapor as they encounter Saturn's increasingly dense atmosphere, eventually mixing with the planet's hydrogen and helium to become part of Saturn itself. As you settle deeper into relaxation, imagine this cosmic precipitation falling perpetually through Saturn's atmosphere, each particle completing a journey that began in the cold outer regions of the ring system and ends in the warm embrace of Saturn's interior. The ring rain is detectable from Earth through its effect on Saturn's upper atmosphere, where it creates a band of increased water vapor around Saturn's equatorial regions. This atmospheric signature was first discovered by infrared telescopes that could measure the composition of Saturn's atmosphere from nearly 1 billion miles away. The water vapor from the falling ring particles creates a distinct chemical fingerprint that stands out against Saturn's predominantly hydrogen-helium atmosphere, providing direct evidence that Saturn's rings are slowly but constantly losing material to the planet below. The detection of ring rain represents one of the most elegant examples of how astronomers can study invisible processes occurring in distant worlds by looking for their subtle effects on observable phenomena. Charged ring particles follow Saturn's magnetic field lines as they fall toward the planet, creating invisible highways of cosmic precipitation. Saturn's powerful magnetic field guides the electrically charged dust and ice particles along specific paths as they spiral inward, concentrating the ring rain in narrow bands around Saturn's magnetic equator. This process creates a complex three-dimensional structure of falling particles that resembles an enormous, invisible waterfall cascading from the rings into Saturn's atmosphere. The magnetic field lines act like cosmic gutters, channeling the ring rain toward specific latitudes on Saturn while leaving other regions relatively dry. The rate of ring rain varies with Saturn's seasons and the electromagnetic environment around the planet. During periods of high solar activity, increased radiation pressure and electromagnetic effects can either accelerate or slow the infall of ring particles, creating seasonal and cyclical variations in the ring rain rate. These variations are so subtle they require years of careful observation to detect, but they demonstrate that Saturn's ring system is constantly responding to changing conditions in the space environment around the planet. The ring rain thus serves as a cosmic weather gauge, recording the effects of solar storms, magnetic field changes, and other space weather phenomena on Saturn's ring system. Different ring regions contribute different amounts to the ring rain, with the innermost C and D rings providing the majority of falling particles. The particles in these inner rings are already close to Saturn and moving relatively slowly, making them more susceptible to atmospheric drag and electromagnetic effects that cause them to lose energy and spiral inward. The dense B ring, despite containing most of the ring system's mass, contributes relatively little to the ring rain because its particles are more stable and less likely to be perturbed from their orbits. This differential contribution means that the ring rain carries a chemical signature that reflects the composition of Saturn's innermost rings rather than the ring system as a whole. Micrometeorites striking ring particles create clouds of fine debris that eventually contribute to the ring rain. These tiny impacts, occurring constantly throughout Saturn's ring system, chip off fragments of ice and rock that are small enough to be influenced by electromagnetic forces and atmospheric drag. The debris clouds created by micrometeorite impacts spread out along the orbits of the impacted particles, creating temporary enhancements in ring density that gradually dissipate as the fine material either reaccumulates onto larger particles or falls into Saturn's atmosphere. This process represents a form of cosmic erosion that slowly wears away ring particles over millions of years. The ring rain affects Saturn's atmospheric chemistry and may influence cloud formation and weather patterns in the planet's upper atmosphere. The constant influx of water from falling ring particles adds to the overall water content of Saturn's atmosphere, potentially affecting the formation of water ice clouds and altering the planet's overall atmospheric composition over long time periods. Some scientists theorize that the ring rain may even influence Saturn's famous hexagonal polar storm by affecting atmospheric circulation patterns, though this connection remains speculative. The idea that Saturn's rings might influence the planet's weather demonstrates the complex interconnections between different components of the Saturn system. Observations of ring rain help scientists estimate how long Saturn's rings have existed and how much longer they might survive. By measuring the current rate of ring material loss and estimating the total mass of the ring system, astronomers can calculate roughly how long the rings have been losing material at the current rate. These calculations suggest that Saturn's rings are much younger than previously thought, perhaps only 10 to 100 million years old rather than billions of years old. The ring rain observations thus provide crucial evidence about the age and evolution of Saturn's ring system, helping resolve long-standing debates about when and how the rings formed. The electromagnetic effects that drive ring rain also create radio emissions that can be detected by sensitive instruments on Earth and spacecraft. These radio signals, generated by the interaction of charged particles with Saturn's magnetic field, create a kind of cosmic radiostatic that varies with the rate of ring rain and the electromagnetic conditions around Saturn. By monitoring these radio emissions over time, scientists can study changes in ring rain rates and gain insights into the electromagnetic processes occurring in Saturn's magnetosphere. The radio signals provide a real-time soundtrack to the invisible process of ring rain, allowing astronomers to listen to Saturn's rings as they slowly dissolve into the planet's atmosphere. Computer models suggest that the ring rain rate has varied dramatically over the history of Saturn's rings, potentially accelerating as the rings age and lose mass. As the rings become less massive and more diffuse, the remaining particles may become more susceptible to perturbations that cause them to spiral inward, creating a feedback effect that accelerates ring loss over time. This modeling suggests that Saturn's rings may be in a relatively late stage of their evolution, having survived for millions of years but now entering a phase of accelerated decay. The ring rain we observe today may thus represent the twilight phase of Saturn's magnificent ring system, a cosmic sunset that will play out over millions of years as the rings gradually fade away. The study of ring rain has implications for understanding ring systems around other planets and possibly around extrasolar planets. The processes that drive ring rain at Saturn likely operate in other ring systems as well, suggesting that planetary rings throughout the universe are temporary features that form, evolve, and eventually disappear on timescales much shorter than the lifetimes of their parent planets. This realization has changed our understanding of planetary rings from permanent features to transient phenomena, making the existence of Saturn's rings during human civilization seem like a remarkable cosmic coincidence that allows us to witness one of nature's most beautiful but ephemeral creations. Long ago, when Saturn's rings first formed from some ancient catastrophe or cosmic collision, they began their slow journey toward dissolution through the gentle process of ring rain. Over vast stretches of time, countless tons of ring material have fallen into Saturn's golden atmosphere, each particle completing its final orbit before becoming part of the planet itself, creating a cosmic cycle of formation, evolution, and eventual return that continues even now as you rest peacefully in the quiet darkness, knowing that Saturn's cosmic rain falls steadily through the eternal night. Chapter 9. The Mysterious Birth of Saturn's Rings. The origin of Saturn's magnificent rings remains one of the greatest unsolved mysteries in planetary science, with several competing theories attempting to explain how these cosmic jewels came to exist. For centuries, astronomers assumed that Saturn's rings formed alongside the planet itself, from the same primordial disk of gas and dust that created the entire solar system 4.6 billion years ago. However, recent evidence suggests that the rings are much younger than Saturn itself, perhaps only 10 to 100 million years old, raising profound questions about what cosmic event could have created such a spectacular structure relatively recently in astronomical terms. As you drift into deeper relaxation tonight, imagine the mystery of Saturn's birth unfolding in the cold depths of space, where ancient catastrophes and gentle accumulations work together to create beauty beyond imagination. The leading theory proposes that Saturn's rings formed from the destruction of a large moon that wandered too close to the planet and was torn apart by tidal forces. This hypothetical moon, roughly the size of Saturn's current moon Mimas, would have slowly spiraled inward over millions of years due to tidal interactions with Saturn until it reached the Roche limit, the critical distance where Saturn's gravity becomes stronger than the moon's ability to hold itself together. At this point, the doomed moon would have been gently pulled apart, its material spreading out around Saturn's equator to form the ring system we see today. The destruction wouldn't have been violent or explosive, but rather a gradual unraveling as the moon's ice and rock slowly distributed itself into countless orbiting particles. Computer simulations suggest that a disrupted moon could produce ring systems remarkably similar to Saturn's current rings, complete with gaps, divisions, and density variations. These sophisticated models show how the debris from a destroyed moon would naturally organize itself into multiple ring bands separated by gaps, as different-sized particles settle into different orbital distances. Based on their response to Saturn's gravity and the gravitational influences of surviving moons, the simulations can reproduce many of the observed features of Saturn's rings, including the prominent Cassini division and the relative masses of different ring regions, providing strong support for the disrupted moon hypothesis and demonstrating how cosmic destruction can lead to the creation of breathtaking beauty. Alternative theories suggest that Saturn's rings might have formed from the collision of two or more moons in orbit around the planet. In this scenario, ancient moons following stable orbits around Saturn might have been perturbed by gravitational interactions with other moons or by the gradual evolution of Saturn's internal structure, causing their orbits to become unstable and eventually intersect. The resulting collision would have shattered both moons, creating a debris field that gradually spread out and organized itself into the ring system we observe today. This collision theory helps explain why Saturn's rings are composed almost entirely of water ice, the material that makes up most of Saturn's moons, rather than rocky material that might be expected from other formation mechanisms. Some scientists propose that Saturn's rings are the remnants of passing comets that were captured and destroyed by Saturn's gravitational field. Comets venturing too close to Saturn during the early history of the solar system might have been torn apart by tidal forces, their icy nuclei shredded into countless fragments that settled into orbit around the planet. This theory could explain the high water ice content of the rings and their relatively young age, as comet captures might have occurred episodically throughout Saturn's history rather than all at once during the planet's formation. The comet capture theory suggests that Saturn's rings might represent the accumulated debris from dozens or hundreds of comet encounters over millions of years. The pristine composition of Saturn's rings provides important clues about their formation, mechanism, and age. The rings are remarkably clean and bright, composed of nearly pure water ice with very little contamination from rocky material or space debris. This purity suggests either that the rings formed recently from clean ice sources, or that they have some mechanism for cleaning themselves over time. The lack of significant rocky contamination argues against formation from asteroid impacts or gradual accumulation of interplanetary debris, both of which would be expected to leave more rocky material mixed with the ice. The pristine nature of the rings thus supports theories involving the destruction of icy moons rather than rocky asteroids or mixed composition objects. Gravitational interactions between Saturn's rings and moons suggest a complex evolutionary history involving both destruction and reconstruction. The current configuration of Saturn's moons and rings appears to be the result of multiple episodes of moon formation, destruction, and reformation, creating a dynamic system that has evolved significantly over time. Some of Saturn's current moons may actually be recycled objects, reformed from ring material that gradually reaccumulated into moonlets, which then grew into full-sized moons through further accretion. This process of ring moon cycling could explain why Saturn has so many small, icy moons and why its ring system appears younger than the planet itself. Chemical analysis of ring material by the Cassini spacecraft revealed trace amounts of organic compounds and rocky material that provide fingerprints of the ring's origin. These minute contaminations, though making up less than 1% of the ring material, contain important information about where the ring particles came from and what processes have affected them over time. The organic compounds might be the remains of complex molecules that formed in the original parent body before it was destroyed, while the rocky material could represent the silicate core of a disrupted moon or contamination from meteoroid impacts. By analyzing these chemical signatures, scientists hope to determine whether the rings formed from one large disrupted body or from multiple smaller objects over time. The age debate surrounding Saturn's rings has profound implications for our understanding of planetary system evolution. If the rings are indeed young, as current evidence suggests, it means that the spectacular ring systems we see around the giant planets today are not permanent features but temporary phenomena that form and disappear on timescales much shorter than planetary lifetimes. This realization suggests that ring systems might be much more common in the universe than previously thought, as planets might create and destroy ring systems multiple times throughout their existence. The temporary nature of planetary rings would mean that we are extraordinarily fortunate to live during a time when Saturn displays such magnificent rings. Future missions to Saturn may finally solve the mystery of ring formation by analyzing ring material in unprecedented detail. Proposed sample return missions could bring actual ring particles back to Earth for analysis in terrestrial laboratories, revealing isotopic signatures and chemical compositions that could definitively determine the ring's origin and age. Such missions would represent the ultimate detective work, using the most sophisticated analytical techniques available to decode the cosmic story written in tiny fragments of ice that have been orbiting Saturn for millions of years. The rings themselves would become witnesses to their own creation, carrying the evidence of ancient cosmic events in their crystalline structure.